In the previous chapter of magnetic fields, we have learned pretty interesting stuff on how you can create magnetic fields and how you can use magnetic fields to generate the Motor effect and get things moving, particles and conductors moving. But the story is not over yet. So if you look at this thing, this is what we call particles moving in the coil, right? Moving pretty fast. And because of all these charge carriers moving in the coil, you have a magnetic field. Okay, we learned how to draw this in previous chapter of magnetic fields. But actually, is there a way to do the reverse? For example, if there is no charge moving, this bulb cannot light up. But what if these charges can move? How? The answer is a magnet can do the magic. So if we somehow move a magnet a little bit, oh, we got a bulb to light up. But only when the magnet is moving. Why is that? So the story continues with Mr. Faraday. In the 1800s, somewhere around 1831, Mr. Michael Faraday said, okay, we have come pretty far away. We know how we can use electricity to create magnetic fields. And of course, you can find the force on conductor. Fleming has done lots of work on that. But is the reverse also true? Can we use magnetic fields to create electricity? So this guy, super free, here's what he did. So he took a hoop, an iron core, not a frisbee like this. He took an iron core and he wound wires around the core. So you get something like this setup. I know he must be very free at home, right? Doing experiments. Okay, so you got an iron ring, wound some copper cores around it. That's one circuit on the left and another one on the right. All right, so something like this. So you have one loop here, another loop here as well. And all he did was flick a switch. On, off, on, off. When the switch is connected, there's current flowing through the wires and back out here. Okay, that's it. So logically, this first coil should not affect this second coil, right? Wrong. In fact, Faraday saw it and he was like, oh! When I hit the switch, sometimes I send a current through this thing, suddenly there will be a deflection on this side. What does a deflection tell you? Deflection says that, oh, wait up, there's also current maybe flowing inside here too, maybe in this direction. Sometimes it changes direction. But how is that possible? There is only current on the left coil, on the left circuit. How is there current appearing on this side? Well, my friends, this is called induction. Current induced in the second coil. So he came up with the law. This guy said, all right, let's come up with Faraday's law of electromagnetic induction. And this is what he said. All right, guys, this is what I observed. You can have an EMF that is induced. Guys, remember what's EMF? EMF, you know, like 6 volts of a battery, EMF. So the EMF induced. This is based on his observation. Induced means, look, they're not touching. Somehow an EMF will appear on this side. Induced, that's what it means, okay? So EMF induced in a closed loop or closed conducting loop. All right. What is the relationship with something? How do you know there's an induced EMF or not? This is what he says. EMF induced in a closed conducting loop is directly proportional to what? He invented this new idea called flux linkage. Change in flux. Technically, he didn't invent it, but proportional to the rate of change of a magnetic flux linkage. That's the word for it. Magnetic flux linkage. And the main idea here you want to remember is E is proportional to rate of change. Remember, we always do like d by dt. So this is magnetic flux linkage. So we usually use this symbol phi. And that is the law that he came up with. So the main things you want to remember when you're writing out this definition for exams and things like that is, firstly, EMF induced directly proportional to rate of change of what? The third part, magnetic flux linkage. Okay, so what is flux again? Let's revise a little bit. So you remember all these magnetic field lines we draw? These are really called flux lines. And we're going to learn more about what flux and flux linkage means. But if you observe this coil here, when I grab the magnet and I start to move it, these flux lines are getting cut by these coils. See how the white lines cross over the copper coils? That's what we call a change in magnetic flux linkage. So now, let's pause a little bit on Faraday's law and look a little bit more about what is flux linkage and how do we set ourselves up to understand this better. So, what is magnetic flux? To prevent confusion, gotta remember a bit, by the way, guys. You all already learned B. That is what we call magnetic flux density. That's the B in the units of Teslas. But now we're looking at magnetic flux, which is a different thing. So how do we... Well, in layman terms, the fake definition for you to understand, it's kind of a way of measuring the amount of magnetic field, if you want to say it that way. The amount of magnetic field that is covered in a certain area. But don't write this definition because there's a proper one. This is just a sort of a way to quantify the amount of magnetic field, including how strong that magnetic field is. Okay, so let's say we have a coil here, a circular coil. Sorry, not circular, a square coil. And you have it at an angle and the magnetic field is passing through it. How do we define magnetic flux? Because Faraday's like, oh, there's this thing called flux and it's changing. Well, we need to define what it is, right? So one way people say is, okay, let's say that this, what is magnetic flux? It is the product of two things, magnetic flux density, that's number one, and the perpendicular area. So what we say, an area normal to the lines of flux. Do I have any more space? Nah, of flux. There we go. So this is how we define what a magnetic flux is. It's kind of a new thing, but we use the logo phi, Greek letter, and product, right? So magnetic flux density times A. But they're really direction vectors. So we're going to put direction vector hats and remind ourselves that this is a dot product. So what that means is, if you want to get rid of the vector, when you have a dot product, this will be BA, and the angle between B and A, which will be cosine of phi. We use this symbol phi. Okay, how do we relate that to our diagram? Number one, we need to know what is B, what is A. B is your magnetic field direction, or where the flux lines are pointing, that's B. So all pointing to the right. But what is A? This is new. Have we seen this before? No, we have not. So A here is what we call the vector perpendicular to the plane. So I'm going to draw it out for you. So if you have some kind of plane, such as maybe something like this, whatever face it's facing, that's your A. So for example here, this is A. It's just to tell you where the plane is facing, alright? So let's just write a reminder here. A is the vector perpendicular to the plane, just to tell you where the plane is pointing. Right? So in this case up here, if you want to draw A, it'd be kind of like an angle like this, perpendicular to this plane. Oh my goodness. Alright? So anyway, if we want to think of the magnetic field together with the plane, if I want to try to redraw this diagram up here, maybe I want to use a different view. So I would say, well, if you have a magnetic field that's pointing this way, this is not going to work because we need to resolve something, because you're a product of magnetic flux density and the area normal to the lines of flux. So we need to do some resolution of vectors over here. Firstly, based on the diagram above, angle theta up here is between the plane A and the magnetic field line B. So plane of A, magnetic field of B. So that will be the angle right here. This is our theta. Now to make sure we resolve everything in the plane of the plane, component of the plane, we make sure we resolve B into two parts. So there's a horizontal and there's a vertical in the frame of the plane. So I'm going to draw a frame of the plane. Okay, we have an x, we have a y. So how do we resolve that? Well, if this is b, then this will be opposite hypotenuse sine. So b sine theta, and this horizontal one down here will be b cos theta. So in other words, we can say, oh, angle between b and a is phi. So that is our first equation that we look at, the angle between b and a. So b and a, phi. But you can also change it to be in terms of theta, like what we do there. So we resolve the magnetic field instead. So you can also have another way of calculating flux, which is BA sine theta. And there's two different angles here, so don't confuse both. And the magic is this: once you resolve your magnetic field, so all the purple color lines, you can say, oh, doesn't matter how the magnetic field is tilted or twisting or turned. I can just say, hey, I have a coil, there's a certain area, and there's all this magnetic field line that is perpendicular, nice and perpendicular. But of course, these are just the components of B that is perpendicular to the area. So that's the convenience of using the second method. If you just resolve the B instead. Okay, so depending on the situation, you might be required to use both. All right, different ways of thinking about it. But here's some reminders. Firstly, this phi right there is the angle between B and A. And these two are vectors. Remember what B is, what A is. Then this angle, theta, is the angle between B and the frame of this coil. So, yep, just know there are two ones. You can choose which one to use, whichever is more convenient in different scenarios. Okay, so product, this is how we define flux. How much magnetic field passing through a certain area that is normal to the flux. Now, one thing for you to think about: how do we redraw this diagram up here to do something like what we've done just now? So if you want to redraw this, you have to think of what view you want to take. So it's helpful when you are doing past years, you know how to redraw in different planes. So let's say I want to look at the top view, and my eye is up there looking down at this whole thing. So how I can redraw is something like this. Maybe I will say top view. Okay, let's draw the magnetic field first, going to the right, something like that. Okay, then I have the slanted frame of the coil. It is top view, by the way, guys. So top view. And I have the angle theta that's given to me. So theta. Let's label that B. So first thing, remember, oh, this A vector is going to be perpendicular to this frame. And the angle between B and A is phi. And don't forget, your B can also be resolved into the plane of the frame. So you have a horizontal and you can have a vertical, and it's all twisted upside down components. So it's something like that, this way and this way. So one will be B sine theta. The other one will be B cos theta. Okay, so we're resolving your magnetic field in terms of the axis of the plane. So it's kind of tilted like that. Tilt your whole axis. But it's all things that you've done before. Resolve components. So we resolve magnetic field. Oh, then you get something like that. So be aware, know how to draw top view, side view, whichever view is more helpful to understand or solve a certain problem, and recognize what angles are which ones. Okay, so moving on. So this magnetic flux density is a new thing. We got to give it a unit, right? So B times A. What's the unit? Weber. Huh? Weber? Well, Weber, Weber. This is the unit for phi, or magnetic flux. How do we define this thing? If they ever asked you in a past year question, all you need to say is, 1 Weber is 1 Tesla meter square. Where did we get that from? Well, remember phi equals to B dot A. B is Tesla. Area is meter square, so 1 Tesla meter square. In other words, this is TM square. That's all you need to know, okay? So remember the unit for it. And this new thing is called flux, which just quantifies how many of these flux lines and how much magnetic field is coming through a certain area. So field area. There's another one that is related called the magnetic flux linkage. So flux is through one area. What about linkage leh? Okay, look at this diagram. What's the difference between the left side and the right side? Here you have maybe one coil connected with wires like that. Yeah, the difference is that on the left side you just have one loop enclosing an area. But on the right side, you have N turns, many coils. And there's a difference between both. So magnetic flux linkage takes into account all the coils, many turns. So on the left, usually we'll say, oh, phi equals to BA. So we write there B. Oh my, things are disappearing. A sine. What is theta? Theta is the angle between B and the area. Okay, so B. In this case, theta is the angle between the frame and the magnetic field line. So this is 90 degrees. All this is 90 degrees, poking right into the area. So this is sine of 90. So this is gone, man. Sine of 90 is 1. So it's gone. So all you have now is the flux. What's the total amount going through this loop? BA. That's it. But on the right side, let's change this up a little bit. Flux linkage takes into consideration every single turn. So you will have, for every loop, a certain area covered, and there are n number of loops. So you can say, instead of just BA sine theta, you're going to go NBA sine theta. But sine theta is 90 also, so we'll just say NBA. Sine 90 is 1. Oh, okay. So NBA, the n just takes into account each loop. So one loop got how much passing through? So if you have many loops in total, multiply all together. Okay, so what if the B is at an angle to your coil? Then how leh? Let me draw for you. So maybe let's say the field is coming through at an angle like this and pokes through and comes out. Like something you skewer in there. So you have a certain angle theta now. And this is your B. What to do? This is the angle phi. So angle theta, so phi equals to, all you can say is, hey, just BA sine theta. It's no longer 90 degrees, so we cannot ignore it. Same thing, if you have many coils, and then you send a magnetic field through it. So this is B. So what is the flux through this area? You calculate NBA, but don't forget sine theta, because now you are at a certain angle to this plane of the area. Let's close this up so it looks more like that. All right. So remember, flux. What is flux? Flux is just something we define to help us quantify the amount of magnetic field, how strong it is, and through what area. So back to Faraday. Now he says, okay, EMF in a closed loop is directly proportional to the rate of change of magnetic flux. Linkage means takes into consideration every single coil of any loop. In other words, he's like saying magnetic flux linkage, right? Total flux. Here, let me write it down here. Magnetic flux linkage is N times 5, aka kind of a way of quantifying the total flux in the whole coil. So he's saying if there's a change through this coil, you're going to have an EMF induced. And that is what we saw just now in the simulation. Now, there are many ways you can change the flux, by the way, because this phi, as we have learned just now, equals to BA sine theta. So in a system or a setup, if any of these change, then you have a change in flux already. Suddenly the magnetic field strength becomes stronger. Wow, change in flux. Suddenly the area change, becomes smaller, become bigger, change in flux. Suddenly the angle change, the thing rotate, we will change in flux. Any of these changes to this setup will cause a change in flux and will induce an EMF, ding ding ding, positive, negative, into the points. Only when there's change. Okay, so we'll look at more examples after this. In fact, this is pretty much almost the theory of the whole chapter, but we will look at many case studies of how there are different ways you can change the flux through a certain loop and cause or induce an EMF. But before we go to examples, one final thing. Lenz Law. Lenz came along about 3 years, I think, I think about 1831, or was it? Oh, that was Faraday. Faraday was in England. He's an Englishman doing his experiments in the lab, and he comes along Lenz, this Russian physicist, and he says, "Hang on a second. There's one thing you missed out, Mr. Faraday, and that is this strange behavior of induced current and EMF." Here's what he noticed. He noticed that the direction of the induced EMF, so give me a second to write that, direction of the induced EMF or current. That's why the light bulb can light up when you send a magnet going through a coil. The direction of the induced EMF or current causes effects. And this is the weird part. To oppose the change, producing it. What is this? What does this mean? The main idea you want to know is oppose the change. Keep this in your mind. Let this sentence marinate in your brain. And in the next few case studies and examples, when we say oppose the change, think of Lenz Law and what he really means. Because it's a bit hard to explain now if I just said, oh, it means oppose the change. What does it mean? Well, hang in there. Keep it in your brain. So there's the equation. He took Faraday's equation and he upgraded it and says, all right, I think this is the final one. EMF that you can induce in any coil is oppose the change, right? So I say negative. A negative there to remind me that it opposes the change in flux. And he says, why not throw in magnetic flux linkage since we are talking about the whole coil setup, right? So N5 is up there and dt. Rate of change of magnetic flux linkage, that's dt. So this is, by the way, EMF, so it's a unit of volts. But this equation is kind of the general idea of the whole chapter. That's it. Okay, you're done with the whole chapter. No. This is in volts. Like, 6 volt, 2 volt, 24 volt. So the whole chapter is just playing around with these two ideas in many different scenarios. So you need to know how to apply to do well in this chapter. Memorizing does not work very well here. The hope is by the end of this chapter and all the example videos, you'll be able to explain things, because explaining is a very big part of this chapter. But here's a bonus video for you to look at before we begin. Now, Veritasium made this really cool video going to Michael Faraday's lab, looking at his stuff and some really cool demos, such as this gigantic coil that has 800 amps going through it and alternating at 900 hertz really fast. And then they are able to make heavy plates of aluminum levitate and like float. So that's really cool for them to be able to do that. And not only that, he even brought a lamp nearby, and the lamp started glowing. Not only that, he put the lamp on the rotating plate and it stayed there. He's trying careful not to touch it because this plate is getting really hot because of very large induced current inside this floating plate. So you see, he start to spray water bottle, some spray, and you see all the steam come out. Okay, so very cool effects and quite mind-blowing to see if you're not sure what is happening. You know what people say? Magic, sorcery, witchcraft, leviosa. But hey, it's just magnetic fields. So see you in the next few examples where you learn about the magic, or I should say the magnetic fields. They've missed out a few words there. Magic minus, magnetic, you take away a few words, it becomes magic. So add those words in there and you will learn how to explain how electromagnetic induction works and apply in all kinds of different scenarios that you will see in life. So that's all for this video. I will see you in the next ones.